Hello everyone. So let's now solve practice assignment week 9 question number 5. Consider a function f of x comma y equal to xy if the directional derivative of f at the point a comma b in the direction 1 comma minus 1 and 1 comma 1 are 1 and 5 respectively, and find the value of 2a plus b by root 2. So now, given our function f of x comma y equal to xy, we can directly find its directional derivative by just doing the dot product between the gradient of the function with the unit vector in which we want to find the directional derivative. So the gradient of the function is y comma x. It is the vector of the partial derivative. Now we want to find the directional derivative in the direction of 1 comma minus 1 and 1 comma 1. But these are not the unit vector, so we need to normalize them. That is, so let's say u1 is our 1 comma minus 1. This will become, if we divide it by its norm, that is 1 by root 2, 1 comma minus 1. And similarly, u2, let's say 1 comma 1. This is also to be divided by its norm. Now we can just do gradient of f at the point a comma b. So here x value would be a, y value would be b. So this would become b comma a. So now directional derivative at the point a comma b with u1, that is our 1 comma minus 1, is given to us as 1. So that is b comma a 1 by root 2 1 comma minus 1 is given to us as 1. On solving this equation we will get b minus, on simplifying it we will get b minus a equal to root 2. Similarly, dot product with u2, that is b comma a 1 by root 2 1 comma 1. Now here it is given as to as 5, and on simplifying we will get b plus a equal to 5 times root 2. This is our equation 1. This is our equation 2. On if we solve this equation, we will get b is equal to and a is equal to. So the value that has been asked in the question is 2a plus b by root 2. So 2 times 2 root 2 plus 3 root 2 by root 2, that is 7 root 2 by root 2, that is 7. And that is our answer. So let's now solve practice assignment week 9 question number 6. Consider the following statements. So we have given a bunch of statements here. Now to contradict all the statement here, we will consider one function which is from R to R and defined like when xy is not equal to 0 comma 0 and 0 when xy is equal to 0 comma 0. Now let's look at the first statement. First statement tells that let f be a function such that limit of x tends to a, limit of y tends to b of f exists where a and b are some real number, then limit of xy tending to a comma b of f exists. Now for that, let's check the limit of our above function when x tends to 0, limit y tends to 0, f of x comma y, and this would be equal to limit of x tending to 0, limit y tending to 0 of xy, x square plus y square. This is same as limit x tending to 0. Now first we will solve this much part, and here we can directly put the value of y to be 0. So we will get to 0 by x square, and that is 0. So this limit exists. Now our first statement is if this limit exists, then the limit xy tending to a comma b exists. That is the limit x comma y tending to origin for the function fx comma y exists. This we need to check. So let's see the limit along the line y equal to mx. So for that 0 for our function f of x comma y, that is x square divided by x square plus y square. Now we can replace y with mx here. So limit x comma y tending to 0 comma 0 mx into x divided by x square plus mx square, and that is mx square by x square into 1 plus m square, with x tending to 0, and that is m square divided by 1 plus m square. So we can see that the limit is dependent upon the slope of the line. So that means for different slope or different path, we will get a different limit. Hence, the limit does not exist. But this limit exists. So the first statement becomes false, as it says if this limit exists, then the limit of xy tending to a comma b exists. But we see that it does not exist. So it is false. Now for the second statement, let f be the function. Now here we are doing the opposite thing, that is limit y tends to b, x tends to a, for the function f of a comma b. If this limit is equal to the function value, then f is continuous. So first of all, we have already seen the limit does not exist at the origin. Now let's look at the limit when y tends to b, or let's say here we are taking the 0, x tends to 0 for the function, and that would be limit y tends to 0, limit x tends to 0, x square divided by x square plus y square, limit y tends to 0, and on solving this part we can directly put the x value to be 0, and then we will get 0 by x square plus y square, and that is 0. So this limit exists, and that is also equal to the function value at the 0 comma 0. So according to the statement, if this limit exists and equal to the function value, f should be continuous, but we just now seen that the limit of xy tending to 0 comma 0 does not exist, so it will not be continuous also. So that means the second statement is also false. Third statement, if limit x tending to a, y tending to b for the function, and limit y tending to b, x tending to a, if this is equal to function value, then f is continuous. We have found out that our both this limit is equal to 0, which is also equal to the function value we just now calculated, and as all three are equal, but as the limit does not exist at the origin, so this statement is also incorrect. Now fourth statement, that is fourth and fifth statement tells that if the partial derivative at x and with respect to y exists, then f is continuous. So let's calculate the partial derivative. So here for calculating the partial derivative at the origin, we will not calculate the partial derivative directly by the shortcut method by treating y as a constant, because our function it is a piecewise function. So to calculate the partial derivative of this function, we will use the raditional approach, that is limit h tends to 0, so f of 0 plus h comma 0 minus f of 0 comma 0 divided by h, f of h comma 0 minus f of 0 comma 0. So this is now f of h comma 0, our f was defined was x square plus y square, when xy is not equal to 0 and 0 when x comma y is equal to 0. So here our x comma y is not equal to 0, so we will use this definition, and with that also this value comes out to be 0 and f of 0 comma 0 is already 0. So it would be 0 minus 0 by h, so we will get 0. So the partial derivative with respect to x exists, but still we know that the limit at 0 comma 0 does not exist, so function is not continuous. Now let's check for the partial derivative with respect to y also. 0 comma 0 plus h minus f of 0 comma 0 divided by h. And here also we will get this to be 0 minus 0 by h, that is 0. So both the partial derivative exist, but still the limit at the when xy tends to origin does not exist, so the function is also not continuous. So the remaining two statement is also false. So the number of correct statement is 0. Let's now solve question number 7. Consider the following two functions, f1 and f2, both are from R2 to R, defined as follows. Then we are defining a matrix which contains the partial derivative of the function f1 with respect to x and y at some point, and then we will have to find its value of determinant of A. So for that we will need to calculate these values. So let's calculate them one by one. So partial derivative of the function f1 with respect to x is, here to calculate the partial derivative we will treat y as a constant. So the partial derivative with respect to x turns out to be y plus 2. And for the same function with respect to y, the partial derivative it will be just x, as this would be just constant. Now here we need to calculate at the point 4 comma 0. So this would be just 2, and here we need to calculate it at 4 comma 6, so it would be just 4. Now same thing we have to do for the f2 function. So here on treating y as a constant, the partial derivative would comes out to be 2x plus 6xy, and with respect to y this would be 2 plus 3x square. Now we need to calculate the partial derivative of f2 function with respect to x at 1 comma 1. So it will be 2 plus 6, that is 8, and here we need to calculate it at square root of 10 by 3 comma 6. 2 plus 3 times square root of 10 by 3 square, so that is 3 into 10 by 3, that is 12. So now we have calculated all the values, so let's put them down one by one. Our first entry, first row first column entry is partial derivative with respect to f1. For partial derivative of f1 with respect to x at the point 4 comma 0, that value is 2. Our first row second column entry is partial derivative of function f2 with respect to x at the point 1 comma 1, and that is 8. Second row third column entry is partial derivative of the function f1 with respect to y at the point 4 comma 6, that is 4. The second row second column entry is partial derivative of the function f2 with respect to y at the point square root of 10 by 3 comma 6, and that is 12. Now if we calculate the determinant of A, it is 24 minus 32, and that is minus 8, and that is our answer. Thank you.